Alright, if you guys could please turn to section 2.3, properties of functions. Alright, I'm going to write out these definitions. A function f is even if, for every number x in its domain, negative x is also in its domain, and f of x equals f of negative x. Okay? Alright. A function f is odd if for every number x in its domain, negative x is also in its domain, and f of negative x equals negative f of x. Alright, what does that mean? Let's look at an example. Determine whether each graph given in the figure is the graph of an even function, an odd function, or a function that is neither even nor odd. Alright, in this case, if a function is even, where's my cursor? If a function is even, it's going to be symmetric about the y-axis. Actually, let me change colors here. Okay, so if you have a mirror image on both sides of the y-axis, you have an even function. If it's symmetrical about the origin, that means it's flipped and twisted over the origin diagonally like this one, you have an odd function. This one, if it's neither symmetrical about the y-axis or the origin, it's neither. Okay? Alright, use a graphing utility to conjecture whether each of the following functions is even, odd, or neither. Alright, if you were to graph this, let me pull out a calculator. If I graph x squared minus 5 graph, that's an even function. If I graph x cubed minus 1, initially you think it would be odd, but this is the origin here, and it's shifted just a little bit down. So it's actually neither. Can you guys see that? Hopefully you guys can see that. If not, ask me tomorrow and we can discuss it further. The origin is here. If it was just x cubed, then it would be odd. But because it's shifted down, it's not perfectly symmetrical about the origin. It's symmetrical about this point here. Y is negative 1. Okay? So that one's neither. 5x cubed minus x. This one is symmetrical about the origin. Okay? Alright, let me write this down. Even, neither, odd. Okay? Verify each conjecture algebraically. Alright, so we have looked at this graphically. Let's confirm algebraically. Change colors here. In order for f of x to be even, we need to show that f of x equals f of negative x. So let's plug in f of negative x and see what we get. I'm going to get negative x squared minus 5. Negative x squared is just x squared. We have the same thing that we started with. So f of negative x is in fact equal to f of x. So it's even. B is neither. This one's odd. In order to show that it's odd, we have to show that f of negative x equals negative f of x. So let's plug in negative x. These are all h's, not f's. F was the first one. Okay. H of negative x equals negative h of x. There we go. So h of negative x is 5 times negative x cubed minus negative x. This becomes negative 5x cubed. It becomes positive. There we go. And negative h of x, well, I just change the sign of everything in the equation. I've got this plus x. These are in fact equal, so we're good. So now we've shown it graphically and we've shown it algebraically. State whether the graph is symmetric with respect to the y-axis or respect to the origin. I'll just write that up here. Switch back to red. Y-axis, origin. There we go. Okay, example 3. Where is the function in the figure increasing, where is it decreasing, where is it constant? Okay, increasing means that going from left to right, it's going up. So like from here to here, it's increasing. I'm sorry. Let me rephrase that. All the way from here to here, it's actually increasing. Okay? So this is from -4 to 4. I'm sorry, to 0. So increasing from -4 to 0. Where is it decreasing? Let's change colors. Well, it's decreasing from here to here. So from -6 to -4. And then from 3 to 6. Okay. And it's constant from here to here. See, from 0 to 3. Okay. Alright, a couple definitions. I'll go ahead and write these out. A function f is increasing on an open interval I if for any choice of x1 and x2 in I, with x1 being less than x2, we have f of x1 less than f of x2. Basically, if the points on the left side are less than the points on the right side, then it's going up. A function f is decreasing on an open interval I if for any choice of x1 and x2 in I, with x1 less than x2, we have f of x1 is greater than f of x2. So basically, from left to right, it's going down instead of up. Okay? A function f is constant on an open interval I if for all choices of x in I, the values of f of x are all equal. So basically, it's just a straight line. It's going perfectly horizontal. Okay, you guys go ahead and try this one. Local minimums and maximums. Alright, here we go. Change colors real quick. A function f has a local maximum at c if there is an open interval I containing c, so that for all x not equal to c in I, f of x is less than f of c. We call f of c a local maximum of f. So basically, if you have a graph and somewhere in the graph there's this hump looking thing, the very top of that hump is a local max. So everywhere else in that interval, every other point is less than f of c. Okay, so this would be f of c, your local max. Likewise, let me scroll down a bit. If you have a function f has a local minimum at c if there is an open interval I containing c, so that for all x not equal to c in I, f of x is greater than f of c. We call f of c a local minimum of f. So once again, if you have something like this, the very bottom of that is your local min. So there's some interval where all other points are greater than f of c. F of c is your lowest point. Okay? So for example, the figure below shows the graph of f. At what values of x, if any, does f have a local maximum? Well, we can take a look. It has a local maximum right here. So a, 1, 2. What are the local maxima? I guess they wanted it like this, sorry. For what values of x is there a local maximum, it would be x equals 1. And the local maximum would be 1, 2. Local minimums would be here and here. So x equals -1 and 3. So -1 and 1 and 3, 0. There we go. Now list the intervals on which f is, list the intervals on which f is increasing, list the intervals on which f is decreasing. Okay, increasing, you can kind of see only half the graph, but it's in your paper also. From here to here, let me scroll up just a little bit. From -1 to 1, it's going up. And from 3 to infinity. It's decreasing from -infinity to -1 and from 1 to 3. I'll let you go ahead and try this one. Alright, I'm going to stop the video here and I'll go over the other half of this section in the next video.